All right. Hopefully this works this time. Okay, so we saw this yesterday in our presentation. We were going to be pushing a box, and the box was going to be a 5-kilogram box. And so this is something that's going to be important. The mass is 5 kilograms. Okay? For the whole time that we're using, or that we're completing this paper, the mass will be 5 kilograms, and it's a box that's being pushed across a frictionless surface with a force of 10 newtons. So there's going to be a couple of different formulas that we're going to have to use. I listed them on the board right there. And we're going to start out with time. So we're going to pretend like we're pushing this box for 3 seconds, starting from 0. So we've got 0 seconds, 1 second, 2 seconds, 3 seconds. And so fill this in as you follow along. The force is going to constantly be 10 newtons. For goodness sake. Yes. Kimberly, you gotta go to the health office right now. All right. So our force is going to be 10 newtons. Yeah, take your stuff with you. It's going to be 10 newtons the whole time. So 10's all the way down. Now, the next part, this is where we're going to have to start using our formulas. If we're applying a force to a box and it's on a frictionless surface, then the box is going to be accelerating. And the way that we calculate acceleration is F equals m times a, right? So our force, we have in our column right next to it, and our mass, we already know is 5. So the way that this equation ends up looking is like this. It'll be 10 equals 5 times a. And then we're going to solve for a. And so to do that, right, we'll just divide both sides by 5. And we get an acceleration of 2. So our acceleration is 2 meters per second squared. Okay? So we're going to need to be able to do that. Okay? To find an acceleration if we know a force and a mass. Since it's a constant force, right? It's 10 newtons the whole time. That means that our acceleration is going to be 2 meters per second squared the whole time. Okay. Now, for the next bit, we're going to assume that the box starts from rest. And so its initial velocity is going to be 0 meters per second. But this box is accelerating, right? And every second, it's going 2 meters per second faster. That's why acceleration's 2. So 2 meters per second means 2 meters per second faster every second. So we have a formula that we use for calculating this velocity, and this velocity is technically a final velocity because the box is accelerating. So our formula for VF is the initial velocity VO plus A times T, acceleration times time. So this first box, when velocity is 0, hang on. Something happened. This first box. No, what happened to my pen? Good. This is our initial velocity. Okay, when time is 0, That's our starting velocity. So for the next one, down, and for the rest of them going down, what we'll have is VF equals VO plus AT, right? And so the final velocity is 0 plus acceleration, which is 2, times time. So this box right here is after 1 second, and so we'll have 2 times 1. And so this one, our speed is 2 meters per second. Thanks. Grab that paper over there. Okay. Now, if we're adding 2 meters per second every second as we go, because of the acceleration, so we added 2 from the first second to from 0 to 1 second. Then from 1 second to 2 seconds, we're going to add 2 more. So it's going to be 4 meters per second. Okay. We could calculate that using the formula above and do acceleration times time. So that's what? Again, 2 meters per second times 2 seconds gives us 4 meters per second. And again, since we're speeding up 2 meters per second every second, after 3 seconds, we'd be going 6. Okay, so that's how we would be filling in our velocity and how our velocity of our box would change every second for 3 seconds. Now, when it's going faster and faster and faster every second, that means it's going to be traveling farther and farther and farther each second also. So our distance that's going to be traveling is going to be increasing as we go. We have a formula for figuring this out, and I don't want to use it because it's this one. XF equals XO plus VOT plus half of the acceleration times time squared. I don't want to use that, so I'm going to erase it. Okay, what we're going to do instead is we're going to use a little cheat method that uses something that I think is a little bit easier to calculate, and so we don't have to have that big old formula. So, as we're applying a force to this box, the box, we're doing work on the box because the box is moving. So you apply a force, you do work. When you do work, you give the thing kinetic energy. So work turns into kinetic energy. That's work done on the box, turns into kinetic energy of the box. And kinetic energy is much easier to calculate. So kinetic energy, to calculate kinetic energy, we're just doing half of the mass times the velocity squared. And we already know the mass, and we just calculated the velocities. Okay, the first one is easy. It's not moving at all, so it has 0 joules of kinetic energy. But let's do the next one down below that. So on the one below that, we have kinetic energy. We don't know how much kinetic energy it's going to get. We're going to calculate it. It's half, which you can put into your calculator, just do 0.5 instead of half, times the mass, which was 5 kilograms, times the velocity. So after 1 second, it's going 2 meters per second. So we're going to put that here. And it's going to be the velocity squared. So that's 2 squared, which means 2 times 2. Right? So when we punch this into our calculator, what we can do is 0.5 times 5 times 2 times 2. Or it's easier for me. I go 2 times 2 is 4. 4 times 5 is 20. And half of 20 is 10. So if you punch it into your calculator, you'll get 10 joules. Okay. Then, for the next one, we have 4 meters per second. And so our kinetic energy is going to be bigger. right? We're going from 2 meters per second to 4. And you might remember, when you double your velocity, you quadruple your kinetic energy. And so we'll see that right here. So our formula, the way we would calculate this, would be 0.5 times 5 for the mass, times 4 squared, which is 4 times 4. So 4 times 4 is 16. 16 times 5 is 80. And half of 80 is 40. So we would have 40 joules of kinetic energy. Okay? So again, we doubled our velocity from 2 to 4. And we quadrupled our kinetic energy from 10 to 40. All right? So just keep that in mind. For the next one, we're going to calculate it similarly, but instead of the 4s, we'll have 6s. And so you guys can do that. But what we're going to do here is, this is where we're using our little cheat to go backwards and calculate. We're going to use our kinetic energy to calculate our distance traveled. So we're going to be going this way to find distance traveled. So, again, the kinetic energy that something gains comes from the work that was done. So for the first one, we did no work because it has no kinetic energy. And so since we haven't done any work, it hasn't traveled any distance. The way that this looks in the formula is we're using the work formula. Work equals force times distance. Okay, and again, we're using our kinetic energy for work. So our work is 0. 0 joules have been done because we pushed for 0 seconds. Equals, our force is 10 newtons times some unknown distance. That's what we're trying to solve for. In this case, we would be dividing both sides by 10. And so 0 divided by 10 is 0. 0 meters. So ask yourself if this makes sense. We pushed for 0 seconds. It's moving 0 meters per second because it hasn't had enough time to start moving. Since it's not moving, it has no kinetic energy. And since it has no kinetic energy, no work was done. And since no work was done, it's traveled no distance. Okay. For the one below it, we will have done 10 joules of work to give it 10 joules of kinetic energy. So again, we'll have 10 equals our force of 10 times our distance, which is unknown. Divide both sides by 10. And we get a distance equal to 1 meter. So after 1 second of pushing, the box is going 2 meters per second and has traveled a distance of 1 meter. Okay, for the next one, we'll be using 40 instead, still using 10 for our force and our unknown distance. And solve for D, and then do the same thing for the one below that. But first, again, we're going to want to calculate that kinetic energy. Okay. The last column is for momentum, and momentum has the formula P equals m times v. That's mass times velocity. Don't know why the P stands for momentum. It just does. This first one, again, is a 0 because it's not moving. It has no momentum. The units are kilograms times meters per second squared. But let's just do the one below that for practice. And so again, it's P equals m times v. To find our momentum, that's the mass is 5 kilograms times its velocity, which is still 2 for this one after 1 second. So 2 times 5 is 10 kilograms times meters per second. Oops, I say meters per second squared over here. I didn't mean to do that. It's just meters per second. These two numbers, this 10 and this 10 being the same, that's just a coincidence. So for the next one, our momentum is not going to be 40. Okay, so momentum and kinetic energy usually won't match. It was just a coincidence they did there. After we have all of this filled in, then we're going to be looking at the relationships of these variables to each other, starting with force and time, acceleration and time, and then velocity and time. So using the numbers in our data table, it says in the instructions right here that we're going to sketch a graph using the first term on the y-axis and the second term on the x-axis. So remember, the vertical axis is y, and our horizontal axis, that's x. Okay, that means that force is going here, and time is going here. For this, all of this data, right, we had 10 newtons, 10 newtons, 10 newtons. So it's a constant force for the whole time. Let's put the time across the x-axis first. We're doing for 3 seconds, starting at 0, then 1, 2, 3 seconds. And it's always going to be 10. There's no scale on this, so we can put 10 wherever we want. We'll just put it right here. 10, that's newtons. Okay. So it starts off with a force of 10. After 1 second, the force is 10. After 2 seconds, the force is 10. And after 3 seconds, the force is 10. And so we want to connect that with a nice straight line. It's showing it's a constant force. For the acceleration versus time, again, the first term is on the on the y-axis. So this is acceleration, and doggone it. And we have time across the x-axis. 0, 1, 2, 3. We could do a better job of that. And our acceleration is always 2. Even from the very beginning, when time is 0, its acceleration is going to be 2. It hasn't started moving yet, but its acceleration is still 2. So we'll put that somewhere right here maybe. And then it's constantly 2. They're not always going to be like this, constant like this. But the first 2 are. So again, we have constant force, and now we have constant acceleration. Okay. For the next one, this will be the first one where it looks a little bit different. It's velocity on the y-axis and time on the x-axis. 0, 1, 2, 3 seconds. And checking back at our data, we see our velocities are 0, 2, 4, and 6 meters per second. So when we're putting this on our graph, we'll have 0 at the bottom line, then 2, 4, 6. Sorry, it's really small. So 0, 0. After 1 second, we're going 2. After 2 seconds, we're going 4. After 3 seconds, we're going 6. And so draw a straight line through there. Now we have this constantly increasing speed. But this is, I don't know, we can just call it increasing speed. Or we could call it constantly increasing speed. Okay. So hopefully that gives you an idea of where we're going with all of this. And if you have any questions, ask your neighbor. And don't forget to like and subscribe and ring that bell. Okay, bye.